Our next speaker is Mr. Laurin Herr. Laurin is from San Francisco. He's going to talk about and show us examples of collaborative content creation using high-speed networks. It is a CineGrid research update. The CineGrid is an association that Laurin actually has created with his partner in San Francisco. Laurin is the founder and president of Pacific Interface, an international consulting company providing clients strategic consulting in digital media technology and business development. As I said, Laurin is the co-founder of CineGrid, which is a nonprofit international research and educational organization pioneering the production, use, preservation, and exchange of very high-quality digital media over fiber optic networks. Laurin worked for 12 years in Silicon Valley in senior management positions at companies making peripheral devices to enable desktop publishing and nonlinear video editing. Laurin has lived and worked for many years in Japan, learning the language and earning a 5th degree black belt in martial art Aikido. Don't want to fight with you, Laurin. Come on up on stage. Please welcome Mr. Laurin Herr.
Thank you very much, Hal, for the kind introduction, and thank you very much to the people of Cyberport for organizing today's event and for inviting me to speak. I also spoke in 2010 at DELF and about CineGrid, but we're just adjusting. You want the display? Okay, we're going to High technology is so easy. Should be mirrored. This is why we rehearsed yesterday. So any of you in the entertainment business know the importance of rehearsal. And we did rehearse, and everything worked swimmingly. So if necessary, I will do tap dancing and hand puppets. Yeah, right, before we invented computers. So my own personal career is, those of you who are students, Richard Cheng gave some very good advice, as did Martin and some of the other speakers this morning. And my advice to you is very similar to theirs, which is go for it and follow your passion. But it really doesn't matter a whole lot what you study in university as to what you end up doing in your career. I was a political science major at Cornell University and had no idea what I was that I was ever going to be doing this sort of thing, and fell into it by happenstance. Can we show my slides? Hey, we did it. Thank you. This is AV support team. So I'm going to speak about CineGrid at DELF, and my name is Laurin Herr, and as Hal said, I'm a consultant by profession, and CineGrid is a nonprofit. I'm unpaid volunteer executive director of CineGrid. CineGrid is a nonprofit international membership organization, a community of networked collaborators. Members pay dues. We use the dues to support small overhead staff, a staff with an overhead, and we have an annual conference. The human community that CineGrid builds is the most valuable and vibrant thing that we have to offer. The genesis of CineGrid really starts here. Now, Richard Cheng showed this morning a picture of himself in 1981 when he was first writing the renderer for PDI. I don't have a picture of myself in 1981, but this is from the same year. This shows Francis Ford Coppola, the famous director, with Dr. Takashi Fujio of NHK Laboratories in 1981, showing the first HDTV cameras brought to the United States. And Mr. Coppola was at the height of his powers. The James Cameron and Peter Jackson rolled up into one of his day. He had done The Godfather, but had not yet done Apocalypse Now. And he looked at this camera and said, oh, I could make electronic cinema this way. Now, it's taken a long time to get there, but we are at that point. Now, 20 years later, this was the first look at 4K, what we now call 4K digital cinema at NTT Network Innovation Laboratories. From the left of this picture, you see a server containing JPEG compressed content, a network, gigabit Ethernet. The big box next is the decoder. That is now shrunk to a board. And to the right, you see an early prototype DILA 4K projector from JVC. And the box in the foreground is the decoder, and the projector control box. Those electronics are now inside the projector. Now, at the same time as that was happening in the media business, this was happening in the world of scientific visualization. A large $13 million National Science Foundation grant in the United States to a number of universities to create what was called the Optiputer, the optical IP computer, where the network was the backplane of the computer. And they had a vision which they could build a room that would include 4K streaming video, gigapixel wallpaper, and augmented 3D stereo reality with no glasses. And they calculated a gigapixel, 3 bytes per pixel, 8 bits per byte, 30 frames a second. They were going to need a terabit per second for a network. This was a vision, not a reality. But they set out with this as a target. And in fact, what I'll talk about is the fact that 4K streaming video is reality, gigapixel wallpaper is reality, augmented reality with no glasses is not yet here, but we're getting close. The other thing that happened is that high-speed networks became available. CineGrid projects run over what's called the Global Lambda Integrated Facility, a network of networks. This is research networks, research and educational networks. This is not a map of the global internet. This is a map of the research networks that are each line representing 10 gigabit links. And using these networks and the cooperation of our members in CineGrid who operate some of these networks, we have been able to form a persistent linkage between CineGrid members acting as nodes using networks supplied by CineGrid members who are network operators. And you can see we have some substantial or major access points in Amsterdam, Chicago, Seattle, Los Angeles, Tokyo, and Sao Paulo, Brazil. We discovered very early on that to do high-quality media over high-speed networks, we needed people who understood picture, sound, networking, computers, storage, screens, audio, speaker systems, as well as a certain amount of show business. And we couldn't find anybody who knew all those things. Some people would know video, but not sound. Some people would know networks, but not AV. And so Tom DeFonte, one of our colleagues at the University of California, San Diego, coined this phrase, learning by doing. And we have used that as a motto for CineGrid, and we do projects, collaborative projects amongst members. The first project here on the upper left was at the international networking event called iGrid 2005, the world's first trans-Pacific 4K live telepresence. That is, we were sending video conferencing at 4K, 4 times the resolution of HDTV, live between the president of the University of California, San Diego, and the president of Keio University in Tokyo. And if you want to ensure that your engineers work really hard, be sure to have your live demo with the president of your university, because it really ups the nerves. In 2006, we did a demonstration at the Audio Engineering Society in San Francisco with a string quartet, student string quartet recorded in Japan, audio sent as files to San Diego, and then streaming from Japan, streaming picture from Japan, streaming audio from San Diego, synchronizing them in San Francisco all over a network, and holding that synchronization through the entire performance of Mozart's Eine kleine Nachtmusik. On the bottom left, you see a live performance that we streamed from Amsterdam, the Holland Festival, to San Diego in 2007 in 4K, a one-woman operatic performance with 5.1 surround sound mixed on the fly. And on the lower right, you see a production we did with the cooperation of DALSA, which was making 4K cinema cameras at the time, to shoot and post-produce in using remote collaboration. This was an homage to the Lumiere brothers, who shot famously a train coming into a station. This was a steam train rolling down the tracks in Prague in the Czech Republic. Now, most digital cinema cameras, like the DALSA and all other cameras that are used today, require post-processing before they can be, the content out of the camera can be used. We did the post-processing. We recorded in Prague overnight. We file transferred content to San Diego, where the debayering was done on a small cluster in the supercomputing center, then sent back to Prague, where it needed to be color corrected. And for color correction, the colorist was in Toronto, Canada. The assets, the color correction system, the screening room, and the director were in Prague. And we discovered a lot from this. We discovered, most importantly, that even though we had 10 gigabit networks, we should not think that the 10 gigabits was only to carry the payload. We needed to use a lot of the network capacity for what are called side channels of communication. Side channels of communication, in this case, being primarily HD video conferencing bidirectional. Also, system control. We were using a baselight system, and it communicated between the control surface in Toronto and the main system in Prague. Now, the people who designed the baselight system very nicely left us a 1 gigabit connector between the control surface and the main system. And we thought, oh, we'll just extend that one connector 7,500 kilometers. And we discovered the system didn't work. And we eventually got an engineer to look at this, and they discovered there was a timeout window as the controller was constantly polling the main system. And they had always assumed the separation would be maybe 100, 200 meters. And when we extended it to 7,500 kilometers, it needed to be changed. And it taught us that working over a distance, we not only needed to have these many side channels, but we needed to check our equipment before we did it. Now, this inspired our colleagues to attempt many other experiments in successive years. In 2009, our colleagues from the Czech Republic once again tried distributed 4K digital intermediate, that is color grading. But in this case, they sent live uncompressed 4K from Prague, streaming over an IP network to San Diego. And what you see here is Felix Nevrala from Cinepost in the Barrandov studios in Prague, standing on the stage in San Diego, working in front of a control surface and a video conferencing system. On the screen, though, is the live 4K uncompressed result from his color correction. So he's telling an operator in Prague what to do, seeing the results in San Diego, as if he's in the same room. So this is a recurring theme. How can we shrink distance and save time by making it possible for people in different places to be as if in the same room? So you've heard a lot today about clouds and working collaboratively, and most of this collaboration is done asynchronously. That is, I send you something, after a while you send it back to me, and we work together that way. And that is extremely convenient, low cost, low bandwidth, and for many, many types of work is sufficient. But what we realized early on, and we set out as a challenge, is how can we be as if in the same room? That means the media has to be of the same quality as if you're in the same room. It has to be at the same time, or close enough to not notice, and it has to be reliable. Can't be stuttering and can't be changing. We did another experiment, this time with the Naval Postgraduate School. We managed to do 8K by 2K, 60 frames per second live remote sensing. This is actually from an aquarium. Dual 4K 60p cameras and dual 4K JPEG 2000 codecs from Monterey Bay Aquarium through the Naval Postgraduate School in Monterey down to the workshop in San Diego. Other colleagues, this time from the University of, from Keio University and NTT Laboratories, worked on multi-point interactive telepresence. Some of these people are, it's very hard to see, but the people in the foreground are standing on a stage in San Diego. The people on the left side of the screen are in Tokyo. The people on the upper left of the screen are in Chicago, and the people in the upper right of the screen are in another place in San Diego, all completely interactive with each other at resolutions that make it feel as if they're in the same room with you. We have estimated that we need about 500 pixels per person on a video conferencing system to feel it as if it's real. And going to higher resolutions, first to HD and then to 4K, enables us to see the other person in such a great reality as if they're there with you. Now, we worked also with Lucasfilm's Skywalker Sound and the Sonic Arts research team at University of California, San Diego to do telecollaboration for audio post-production, real-time picture and sound editing synchronized over IP networks separated by about 900 miles, about 1,000 kilometers. And the key thing for audio is that while we all think, oh, the picture is a very data intensive, very heavy payload, where the audio, it's not so much. An audio engineer, and I've had to learn this myself, audio is extremely intolerant to jitter, that is change in time, and musicians and audio engineers need a very precise latency and synchronization to work together. And so this team worked on the latency budget, managing the latency budget. Latency is incurred at many places in digital production flows. Every device has some level of buffer. A projector has a buffer, a camera has a buffer, an audio mixer has a buffer. And when you work with audio, even the air you incur latency as the sound waves travel to your ears. And they manage this completely as if they were in the same mixing suite, except they were separated by 900 miles. This led to an invitation from Walt Disney Studios to demonstrate how all of these techniques could be brought together into a single room to make a collaboration environment for cinema post-production. And in 2010, we went to the Disney Studios and we basically converted a theater into an interactive collaboration space with the cooperation of not only Disney and Skywalker Sound, but also Digital Domain and Laser Pacific, NTT Labs, University of California, San Diego, University of Illinois in Chicago, and my own company, Pacific Interface. This was a complete success, both technically and politically, such that the Disney management authorized the building of such a room, which is opened in December of 2012 on the Disney lot. Now, in 2011, we, as a community and as a worldwide population, went through the devastating earthquake in Japan, 9.0 earthquake, and followed by a tsunami and the nuclear disaster. And our colleagues at Keio University Graduate School of Media and Design, the students spontaneously, from their heart, decided to make a documentary about what was happening in the Tohoku region of Japan. And however, they had no assets. They weren't at Tohoku when the earthquake happened. They didn't have reporters there. And so they started to crowdsource the content. They went and searched for people who had taken pictures, people who had eyewitness accounts, people who had recorded what had happened. And they produced a documentary, a very moving documentary called Lenses and Landscapes. This led to a desire to produce another documentary, this time in collaboration between the same students at KO and the students at University of California, San Diego. This was called Places and Perspectives. And we took this up as a CineGrid project specifically to explore international collaboration for the creation of a documentary. So student teams, one in Tokyo, actually in Yokohama, and one in San Diego, who had never met. They didn't know each other, they had never met. Their professors knew each other, but the students had never met. And they set out to make a documentary from concept to completion. Writing it, what should we talk about, what should the documentary be, how should we shoot it, what's the storyboard, how do we edit it, how do we do the graphics, the animations, the titles, how do we mix the audio, and they made a very beautiful piece. We used for this facility built in San Diego called the V Room, or virtual room, and we attempted to combine traditional production tools, editors and sketching tools and so forth, with emerging new tools for media sharing, review, and critique, such as the V Room itself, CineSage, which I'll talk about more in a minute, and Pix System, which is a software as a service product specifically for collaboration in cinema production and post-production. We use cloud servers for media transfer and storage, and we use multi-channel 4K and HD video conferencing for face-to-face discussions, for context sharing, and for project development. And I have just a short clip to show you.
Displacement.
No, exactly, yeah.
Right now, when I go home.
American style というか
Philippine days.
Good experience.
And I like it even more now.
I like it here.
So on the 31st of January, 4 short weeks ago, we pulled together some visual arts students from UCSD with the fabulously hard-working graduate students from KMD, and we began a new iteration of Growing Documentaries.
We're going to talk a little bit about how Sage can be used, and we're going to demonstrate that.
And so what you're seeing here is the V Room. Now, we had a talk this morning about how it's important to drive the costs down for startups so that anybody can create anything anywhere. This is not that approach. This is an exploration of what technology, what new technology can be brought to bear in an idealized academic environment to explore the potential when bandwidth is abundant. We are running over 1 gig and 10 gig networks between Japan and the United States here. We have a room which has not only a 32 megapixel wall on one side, but touch screens on another, 4K teleconferencing, and 4K projection. And what we have realized, of course, is that some things are good for storyboarding. Some other environments like this is very good for storyboarding. Other environments you need critical viewing and only a projector will suffice. And this is, they're presenting in this scene, they're presenting to a conference about their project. Now, in 2012, we did another project at CineGrid, this time with the cooperation of the Netherlands Film and Television Academy and the Dutch Supercomputing Center, SARA, in which we experimented with directing remote live shooting of virtual set acting with the live compositing done in the cloud. So the live action camera, and so let's see if I can do this. We have no laser pointer? No, okay. Well, you see a woman in pink standing looking onto a beautiful valley. She's on a green screen in Amsterdam, and the beautiful scene behind her is composited in. In the foreground on the right, you see Harry Schuer, the professor from the Netherlands Film and Television Academy, and he's looking at a video conference, a video feed of the shoot. So what you see there is the green screen with the camera crew facing the actress. Oh, thank you. This one here? Okay. So here's the, well, you can't see it anyway. Okay. Here's the setup. So in the upper left, you have the NFTA in Amsterdam with the green screen. They're using Lightcraft, a kit on their HD camera. The Lightcraft kit reports or produces telemetry from the camera, positioning, zooming, irising. All of this camera data is then, together with the video signal, sent to the supercomputing center on the far right over a gigabit network inside Amsterdam, where it's composited with a rendered scene, and then the result composited image is sent via another network to San Diego, where we're watching this. And let's see if we can show you this clip.
Are you ready?
Nee, moment. Iedereen klaar? Ja.
Robin. Oh yeah, yep. Okay.
Sorry.
And action. First you see the green screen version.
First we're going to see it with the green screen, no composite.
This is the really physical boundary of the studio. Okay, thank you. Can we go back and then do the same scene, but then with the virtual setting this time?
We gaan nu iets verder, Harry.
Okay.
We gaan nu door de deur heen.
Yeah.
It turns out for remote collaboration, it's often very helpful if the director speaks multiple languages, in this case Dutch and English. And you might ask, well, why go to this trouble? Well, sometimes the director is in a different place from the actors. Or sometimes the director just doesn't have the time to go to that location and needs to be someplace else. So let's watch it now with the compositing.
Wij zijn klaar, Harry.
Yeah? Yeah. Okay, ready? Robin, could you remove your hand, please, a little bit? Okay, there you go. And action.
So one of the purposes here is not only to show the technical feasibility, but to teach the students how to work in this new environment. Because it's one of the mission of CineGrid is to train and educate the next generation of media professionals, because the film schools are not keeping up with the technology. Now this is, I'm going to digress here a little bit and talk to you about how we're using some of the technologies developed for scientific visualization in the cause of media. And because what we discovered early on is that the scientists and the film producers have similar problems.
As we generate all this data, I'll just give you one example of many kinds of repositories of the data, this being the Protein Data Bank, which the National Science Foundation has funded for over 40 years. People don't think the NSF will stick with something. This has been done for, I mean, there are what, 85,000 three-dimensional structures of proteins. And here you can see the users around the world. And we heard a talk about this on Tuesday, and there's something like 100 simultaneous users. And so the bandwidth, as these structures get bigger and bigger, of being able to get this out to the end users and also to mirror and keep synchronized remote copies of this so we don't have a disaster that goes down. This is critical, and you can see all these different forms of data that are possible. But again, as we go into a world in which nanotechnology and the technology of biology, the proteins and so forth, merge, the ability to get those detailed structures are going to be critical. So the final one, of course, is the big one of all, and that's the Large Hadron Collider. And we heard from Harvey Newman about the extraordinary amounts of data, but I just want to show you these instruments. Probably, I don't know, hundreds to 1,000 top physicists worked on creating designing and building each of these instruments. And these things are producing prodigious amounts of data. And in fact, you can see here was the signature of the Higgs, which is one of the great discoveries of the last 100 years, was made through data and computation that comes from these instruments. And if you look at the actual bandwidth coming off of just one of these CMS, this is in megabytes per second, and this is 3 gigabytes per second, okay? That's coming out of it, and then it's going around this optical network to the world. So if you come back to this, the microscopes are generating the data. The physics department is receiving the data. The genomics lab and proteomics labs are generating the data. The protein data bank, people are coming into the campus to get the data. So think of these flows just in all different directions of big data requiring this kind of infrastructure.
Now, if I were to replace his words, instead of microscope, I said 4K 60p camera, and instead of a supercomputing center, I said post-production facility, the basic logic of what he's talking about, which is the need for high-speed networks to move this data around so that it can be used, is the challenge, or one of the challenges facing cinema production today. Now, the scientists and let's call it the scientists and the Hollywood people are facing similar problems as we go to digital technology. As long as they were analog, they were really separate worlds. But as we use digital technology, they are facing the same challenges of networks aren't fast enough, storage is not big enough, computers are not fast enough, and where do I get the trained people who know how to use all these tools? Well, if you take this idea a little further, we saw a lot about gaming this morning, and most games, of course, are one-person games. And I think we saw a picture of an Oculus Rift head-mounted display where you can put the goggles on your head and see a 120-degree field of view in HD, actually 720p resolution. This is a facility built at the University of Illinois in Chicago, which does that except for 20 people at once. It's called the Cave 2, and it is a 72 megapixel environment designed as a cylinder. If it's a full 3D stereo, in which case it's 34 megapixels, it has many channels of optical tracking and 20 channels of ambisonic audio. And it is connected not to a 10 gigabit network, but to a 100 gigabit network, which is the next generation of internet technology. Sorry. It is one of the premises of CineGrid is that the scientists and the movie makers can learn from each other. And we can see that this technology that people are using can be, you just saw several applications of science, but one of the grad students was more interested in doing this. So this is a one-to-one model of the StarTech Enterprise from the Wrath of Khan, and he also modeled the interior of the bridge of the USS Enterprise, or the NSS Enterprise, pardon me. So I can imagine, and they are playing games in this space already. This university teaches gaming, amongst other things. Now, we saw a wonderful presentation at lunch about archaeological and cultural heritage projection systems, and I added this to the presentation as a result. This is, in the same environment, the temples of Luxor in Egypt. These are photographed using stereo cameras on a tripod, and the camera steps around 360 degrees and the software stitches the photos together. What's different here is it's projected, and this, while we're looking at video in monoscopic, this is a full 3D rendering and head tracking. So the head tracker in this case is on the camera, and so as the camera moves, the perspective of the viewer changes relative to the picture. And we have seen applications for this technology in archaeology, as well as cultural heritage, and gaming, and science, and medicine, and I believe in entertainment. Now, I'm going to shift back now to the entertainment industry, and one of the most important things we see going on right now is the advent of 4K, and particularly not only in cinema, but with the development of what's called ultra-high definition television, UHD TV, coming now to your home, both for home cinema and for home gaming. This was me standing in Shinagawa Station in Tokyo last October when Sony made public its first advertisements for its Bravia line of 4K televisions. Now, they announced a $25,000 84-inch television at this resolution, and a number of people have purchased it. But last week at a trade show in the United States, they announced a 65-inch 4K television that costs $7,000 and a 55-inch that costs $4,000. So prices are coming down sharply. Well, why is more resolution better for television or for cinema or for science? Because more resolution, especially in entertainment, allows closer viewing of a larger image. And closer viewing of a larger image increases the viewing angle, the angle that you see. An increased viewing angle produces a stronger emotional response. Film directors have understood this forever, as have painters and other types of artists. And what you see here is that HDTV in the upper right, with 2 megapixels of resolution, ideal picture viewing distance is 3 picture heights, gives you a 30-degree angle of view. UHD TV, or 4K, with 8 megapixels of resolution on the screen, is best viewed at 1.5 picture heights away, or rather, another way to say it is you can come all the way to 1.5 picture heights and still not see any structure of pixels or sampling in the image. And you get a 60-degree field of view. NHK Laboratories in Japan has been developing what's called 8K, or also known as UHD TV, which is a 32 megapixel image, that is 8,000 by 4,000. In that case, 3/4 of a picture height, an IMAX kind of experience, is possible with a 100-degree field of view. And they did demonstrations from the London Olympics very successfully. Well, this resolution is leading, as one of the factors leading to the growth of data in the entertainment field. The conversion to digital formats has fueled this increase in media data. A TV show in HD resolution generates about 30 hours of media at 200 megabits per second, or 2.7 terabytes. A season of such shows would therefore produce about 60 terabytes per show, per season. If you make that in 3D, the storage requirement doubles. Make it in 4K, the storage requirement quadruples to a quarter of a petabyte, or 250 terabytes rather. Now, a movie in the DCI specification, Digital Cinema Initiative's Hollywood specification, generates 1 to 2 petabytes per title. 3D, if you make the movie in 3D, doubles that. If you go to what's called high frame rate, such as pioneered by Peter Jackson in The Hobbit, or talked about by James Cameron for his next avatars, you can double or even triple the size of the data, potentially to 10 or 15 terabytes per title. And every time the sales department comes to the producer and says, oh, great news, I can sell this to iTunes. No, I can sell it to Netflix. I can sell it for smartphones. I can sell it, smartphones for iOS. That does a different format compression from smartphones made by Android, running Android system, and that's different from web viewing. And it turns out that the number of distribution channels is expanding. Well, that's good for producers and good for consumers, but they're all different. And this is meaning that you're accumulating more and more data as each one of these streams has to be encoded differently. So even if 1 to 4 megabits per second, which is heavily compressed, a 1,000-hour library of content can generate 0.5 to up to 2 petabytes of data for each distribution deal that you cut. Well, look at these numbers are starting to add up. So this is in the light brown is TV shows and the dark brown are movies. And this is just from the Hollywood studios. And what they're predicting, as you can see here, is that by 2016, they'll be reaching about an exabyte for each, that is 1,000 petabytes of movies and 1,000 petabyte of TV content that they are going to archive. And this is leading to 3 big challenges for the studios. Where do you put all the data? That is, how do you store it? How do you pay for that storage? Where do you get the electricity to run it? How do you archive the data? Film archives very nicely. You keep it cool, dry, and dark, and it'll last for 50 years, maybe even 100 years. Digital data is not so easily archived and requires, using today's technology, an endless migration from today's storage media to the future storage media. And that means that it's much more expensive and complicated to archive digital data. And this is an unsolved problem. And we have file format anarchy. It used to be that if you worked in television, you were probably going to use some tape format made by Sony or Panasonic. And in fact, they fought over these tape formats. VHS versus Beta for the consumers, but in the professional space, we've had maybe 30 different videotape formats between 1960 and 2000. And in the file-based workflows that we have now with digital cameras and digital production, this has gotten only worse. Every camera has a different file format. Every camera has a different data structure. And in many cases, between the same model, same manufacturer's cameras, it can be different. Now, there's a lot of work underway. Many people in cinema use the DPX file format for uncompressed, but this only goes to 10-bit accuracy. And so there's been a movement underway led by the Academy of Motion Pictures and supported by a number of the major post-production houses to use what's called OpenEXR, which is a 16-bit file format, which can handle all the dynamic range and resolution of a modern digital cinema camera, but only increases the storage requirements even further. Now, one other very important trend that we have to look at, and it was mentioned earlier today, we had a very nice presentation this morning about the riches waiting to be exploited in selling gaming to the smartphone user community in China. And I'm not a gamer, and so I can't comment on that, but this is a piece of technology research from Cisco, which basically looks at the data traffic on mobile devices worldwide. And what they're basically forecasting is a 66% compound annual growth rate, better than 2x per year, such that by 2017, they expect 11 exabytes of data to be transferred over mobile data networks, and that they predict that by 2017, 70% of that traffic will be video. Who is going to store that content? How is it going to be distributed? How is it going to be managed and tracked? How is it going to be monetized, that is, sold and collected? Who's going to do the billing system? These are unanswered questions that need to be explored in order to have the entertainment industry reach into this new distribution market. Now, I have one last piece of video to show you, and that is an interactive, live interactive remote collaboration, what's called a telematic music performance. Doing remote collaboration over networks is challenging, but it is nowhere more challenging than in live music collaboration, because musicians need to hear each other close to synchronously, close to exactly at the same time in order to play together. And what I'm going to show you here is a performance done between the University of California, San Diego and the University of California, Irvine, which is separated by about 85 miles. Now, in network time, that's about 20 milliseconds round trip time. The system that you're going to see uses video conferencing. In this case, Life-Size, a manufacturer named Life-Size has a software component that's called Soft Phone, uses H.263 compression, and to send HD video between the two sites. But the engineers that worked on this used open source software called Jack and JackTrip running on Macintosh computers to send audio over networks. The audio itself is uncompressed, the video is highly compressed. It turns out that uncompressed, you have lower latency and higher quality, but you need more bandwidth. Compression gives you less, the ability to work in less bandwidth, but it adds latency and reduces quality. And this is an eternal trade-off that we face. In this case, the lower latency audio transmitted between the two sites in only 22 milliseconds latency, whereas the video took 300 milliseconds. But since they're doing a musical performance, priority was given to the low latency audio. So this is a short piece. These people are playing live and separated by about 100 miles. I hope that what you just experienced is a real musical performance, a real collaboration. The technology was transparent, invisible. They were just musicians playing together. Now, I was in the room when this was recorded, and people broke into applause. It was a very emotional performance, a memorial for a friend who had passed away. But the beauty of it is that they were able to do it. The bass player says he got into doing remote performance because his double bass is too expensive to carry on the airplane. And this is a factor. When orchestras travel, it's very expensive for them to move. They have all their instruments, they have 30, 40, 50 people, and many of them are unionized and have rules and regulations about how much they're paid even when they're traveling. So if it's possible to do music performance remotely over the network, musical collaboration over the network, it is actually possible to do almost any other type of collaboration because it is the most difficult thing to do. In closing, I want to say that collaboration over networks, whether it's in entertainment or in science, whether you're making pictures or you're making music, it's really about the people. The networks can tie you together. The systems can be integrated to work transparently, all to the benefit of the human interaction that is the essence of collaboration. The most important thing that CineGrid has tried to build over the last 10 years has been a community of people who want to work together. The human connections underpinning the fiber connections are the great treasure of CineGrid. We have an annual conference. Anyone is welcome to attend. The next conference will be on December 9th to 11th in this coming year in San Diego, California. Further information can be found on our website. Thank you for your attention.